Hi, my name is Shihao Ban, and let me introduce my project, which is deep reinforcement learning in self-driving car. So let's start. First of all, let me introduce the framework as I do the research from the article 1. Following the model described for DRL, they propose a pipeline framework for the end-to-end training of the DNN for self-driving, as illustrated in Figure 1. The input are the states of the environment and their aggregation over time. And the output is driving action. So we discuss each part in details below with reference to a higher-level block diagram in Figure 2. So let's see the Figure 1 and Figure 2. This Figure 1, as I said, is separated into two parts, the temporal part and spatial part. And the Figure 2 is more details about the spatial features. So let's talk about the spatial aggregation. The first step of the pipeline is the spatial aggregation network. This state contains two networks, the sensor fusion and the spatial features, right? As we can see here, the sensor fusion network and the space feature network. For sensor fusion, this way of presenting the raw information to DNN depends on its ability to extract relevant features, make sensor fusion a network task in the course of learning process. So the result is the CNN is the best suited to this part of the pipeline. And as we discussed above, we have the sensor fusion representation, right? And we also got the CNN method. For the last part, we got the fusion sensors representation enable further processing of the data, focus on important part that is relevant to the driving test. The best use of the value of attention models is recommended to reuse the idea of attention and glimpses network rather than applying an attention filter. So that's this kind of a conclusion, right? But yeah, as we can see, those three can combine to the spatial features. That's the Figure 1 and Figure 2. And we also got the top part, which is the temporal part, right? The traditional algorithm for tracking and localization, like Bayes filter, try to handle such situations through information integration over time. However, such algorithm has still derived under the framework of MDP. Moreover, the traditional signal processing approach like Kalman filter requires manual turning of its model. Alternatively, the current neutral network RNN is able in theory to model long-term dependency on previous states in addition to current observation. So right here, we just talk about some algorithm, maybe try to figure that out, but they also have some disadvantages, right? So as RNN, in practice, due to the limitation of the back propagation of gradients through times, RNN is not able to memorize long-term dependencies. Hence, as the LSTM network are supposed to solve such an issue, right? Right here is LSTM, right? It can able to control which information to keep from the previous states, in addition to which information to forget. Additionally, LSTM control what are add to the hidden states from the new input. So this table is the equation of those those filter, and it's a comprehension. It's a of those states function. Yeah, we can see the RNN, Kalman, LSTM, GRNN, right? And here's the equation. And for the last part of our end-to-end pipeline is the reinforcement learning planning part. This network follows the same training procedures of DQN, with a Q network on the top having the same objective function as described in DQN section. Yeah, as we learned in our class. In case of continuous action, the DDAC network can be used as discussed in DDAC section. The same error is propagated through the network structure to obtain the gradients at every network layer. So that is the end of our framework. So let's summary. We use the Lian keeping assistant algorithm as a sample application to simulate the test and propose framework on the open source racing car simulator. Screenshot shown in figure 3. To be able to use simulate sensor, we use the RCR, SCR add-on, which gives a set to car control and car states. In terms of simulation setup, the input to the network is the track pulse sensor input, which provide the position of track border. In addition to the car speed and exposition, the output are the steering, the gear, the acceleration, and the brake value. The network is trained end-to-end following the same objective of DQA. So this is the whole summary. And yeah, right here, I just finished my service on Arctic 1. But after that, I have some thought that I just think, is that enough? Because it's just maybe not so fit into the real environment, right? So yeah, the model above cannot deal with a situation like choosing to turn left or turn right in the upcoming crossroad, deciding when to leave a traffic circle or towards which path destination to go. Therefore, we have then another article 2, propose a new deep reinforcement learning article that suppose external command as high-level input. That's what we call the SDRL. They apply the SDRL architecture on the DDPG, right? And to use the CALA, a realistic driving simulator as a testbed environment to train and to experiment the new model. So that is the whole things of this, what they do, their work in Article 2. And the result is that their conclusion is that the SDDPD model performs well on the road and responds correctly to the external command that allows the driving agent to take the right turns. Yeah, so let's just talk about the DDPG. The DDPG is an end-to-end off-policy DLL algorithm for continuous action space based on actor credit architecture used for final control. It's component of 2 distinctive but connected neutral network. It is actor and the critics, right? So from this figure, we can see that here's our environment, yeah, and here's the action we output, and here's the DDPD model. Yeah, it can have the actor and the critics. It's pretty straightforward. So to be more specific, yeah, this is just an ideal. That's just an idea, but to be more specific, the DDPD predict an action, the action for current state, and minimize separately 2 losses, and learn and deterministic target policy. The DDPG reuse the DQN tricks. So I won't go through all of those DQN tricks. So yeah, so let's just go on. As I just showing my slides, but I will go For the stair DDPG, the SDDPG will support the external command to show the right direction to the car while driving. The FDDPG, the architecture of the actor and the critics and neutral network are the same for the virtual features extraction. That's use 3 blocks each of which contains a convolutional layer, a batch normalization layer, and a redo activation layer. So we can see this is the actor layer, and this is the critic layer. So also have those, those layer, right? So for the SDDPG, for the experiment, we use the 3 models as we train and test CARLA on 2 different surfaces. For external combined with human input. So this figure shows us both scenario of injecting external combined on DDPN model, right? Here's the 3 model. Thus we have the DDPG, this SDDPG1, and SDDPG2 in different scenario. And let me introduce before I introduce our experiment, which is the most important part. Let me have a short introduce for the CALLA. CALLA is a realistic driving environment developed by this center along with this lab and this institute and built on the top of this game engine and support the camera's raw image and provide direct measurement such as forward speed and orientation. Yeah, here's a picture of that. Yeah, here's this most important part, right? We assess the performance of the resulting 3 saved model and test their capacity to reach a given destination by running them 100 episodes on 2 different circuses, right? The town 1 and the town 2, right? Now here we can see this is a map and this image of the simulation. And so with the 3 engines have to drive to the same destination point, and they will use the same driving condition for both town 1 and town 2. And right here is the same condition they are used, right? The same driving condition. And that's the result. Clearly, the DDPD scenario 2 is the best, right? It's success to leverage the capacity of DRL technology and at the same time allow interpreting the seamlessly internal control command without provoking great perturbation in the car driving behavior. So which is very encouraging to test it in the real world as a next step using the scaled down track with an embedded computer. So this kind of like the conclusion, the results that we can draw from the article 2. Let's summary. At first, right, we just discuss a pipeline framework from end-to-end training of a DN for self-driving. Right, remember this figure, right? We separate into 2 parts: the spiral part, the temporal part, right? And I have to say that framework is very important because it's let me know the foundation of the DNN for self-driving. So then I just think it's not enough, right? I have to test it in a more environment near the real life, right? So we talk about the STDPD model, which perform well on CALLA testbed environment and respond correctly to the external command that allow the driving agent to take the right turn. So even that, I have more thoughts. even if we have the new SDLL show good results, it's not enough to adopt in the real world. Unless the successful rate is near 100%, since the safety and security of people are concerned, which offer a new opportunity to the progress and open widely the field of research for new idea and breakthrough to find the model, find the T model, right? That will perfectly drive the roads and will allow to reach the SB level 5 autonomy. So right here, my my presentation is finished. Yeah, thank you for listening. And